14 inches of silicon carbide single crystal, grown on a furnace no export list would have released, up from 12 inches the year before. That 2-inch shift adds roughly a third more usable area to every wafer sliced from the boule, and the company that achieved it, Tiancheng, built the equipment itself. The prior reading was 12 inches, produced on machines that still carried foreign ancestry in key subsystems. The new reading is 14 inches, produced on proprietary gear, confirmed by company disclosure in 2024. Two readings, 2 inches apart, and a self-sufficiency figure that sits at roughly 20 to 30% and has not moved as fast as the crystal has. The bridge is short. This script reports the diameter, the furnace, the substrate gap beneath it, and the price war pressing against all three. Silicon carbide grows as a single crystal through a process called physical vapor transport. A source material is heated inside a sealed furnace until it sublimes, passes directly from solid to vapor, and that vapor travels across a thermal gradient to a cooler seed crystal, where it redeposits atom by atom and the boule grows. The physics are published. The precision engineering is not. Controlling a thermal gradient uniformly across 12 inches of growth face is hard. Controlling it across 14 inches, on a furnace whose reference design no foreign supplier provided because the sale was blocked, is harder. The diameter is the instrument reading that proves the gradient problem was solved. The economic reason diameter matters is geometric, not linear. A silicon carbide boule is a cylinder. Every wafer sliced from it is a disc. Scale that disc from 12 inches to 14 inches and its cross-sectional area grows by roughly 36%. Think of a circle of dough. Roll it 2 inches wider and every cutter pressed into it yields more pieces from the same rolling effort, the same furnace time, the same seed crystal, the same growth cycle overhead. That 36% area gain is why substrate economics track diameter so closely. More usable die per boule at the same fixed cost of energy, time, and consumables. That is the number behind the number. The 12-inch reading belonged to 2023 and to an era of mixed provenance. Domestic Chinese crystal growers were working with physical vapor transport furnaces that had foreign components in critical subsystems, heating elements, gas flow controls, seed chuck assemblies sourced before export restrictions tightened meaningfully. 12 inches was the domestic high-water mark under those conditions. It was a real achievement, and it was also a ceiling set in part by what imported tooling could reach, not only by what domestic engineering had mastered. 12 inches. Then. The 14-inch reading is 2024, and it is categorically different in one respect: the furnace. Tiancheng's disclosure describes equipment that is proprietary and domestically developed, with no confirmed foreign subsystem dependency in the growth furnace used for the record boule. That is not a minor distinction. The 12-inch result was achievable because purchased tooling at its limit could support it. The 14-inch result required re-engineering the precision layer of the furnace from the constraint outward, because the constraint was the reason the foreign furnace was unavailable. The export control aimed at freezing the diameter reading was the mechanism that produced the new one. The wall redirected the engineering effort, and the furnace is the artifact that records where that effort landed. 14 inches. Now, the area gain translates directly to cost. More die per boule means the fixed overhead of crystal growth, the furnace depreciation, the energy cost, the operator time, the seed crystal, is divided across more finished substrates. At the volumes Chinese electric vehicle inverter and fast charger manufacturers are running, that per-unit cost reduction is not a marginal efficiency gain. It is the number that decides whether domestic SiC substrates can undercut the import price or only approach it. That is the context in which the 14-inch result lands, a market already in price compression, where cost per die is being argued over at fractions of a margin that was never large. The furnace is the durable part of this reading, and it is worth holding that distinction carefully. A crystal diameter can be matched. A competitor who solves the gradient problem on a different machine, or licenses a furnace design from a third country, or simply runs more growth cycles to accumulate the process knowledge, can approach 14 inches on a different timeline. What does not reset is the accumulated engineering embedded in a furnace design that no foreign supplier was available to provide. That design can be replicated inside the domestic supply chain, refined across subsequent generations, taught to other growers, and scaled without reference to an export-controlled platform. The crystal is the proof the furnace works. The furnace is the harder count. Beneath the crystal headline, the substrate self-sufficiency figure reads differently. Analysts tracking import flows and domestic production disclosures estimate that Chinese device manufacturers sourced roughly 20 to 30% of their SiC substrates domestically in 2024. The rest came principally from Wolfspeed and a smaller number of Japanese and European suppliers. That 20 to 30% figure represents a gain from a baseline that sat below 20% in the 2021 to 2022 period. The bulk of substrates were imported then, and the bulk still are now. The crystal record and the self-sufficiency figure are measuring two different things at two different positions in the same supply chain, 20 to 30%. Still, the distance between those two readings, 14 inches on the Boule, 20 to 30% on the substrate supply, is explained by what sits between crystal growth and finished substrate. Slicing a silicon carbide boule requires high-precision wire saws operating under significant mechanical stress on one of the hardest materials commercially grown as a single crystal. The hardness that makes silicon carbide valuable in power semiconductors is the same property that makes each slicing pass slow, expensive, and potentially defect-generating. After slicing, each wafer requires surface grinding, then chemical-mechanical polishing to sub-nanometer flatness tolerances, then defect inspection at production volumes. Each of those steps has its own equipment supply chain, its own chemistry supply chain, and its own yield curve. The 14-inch crystal is the upstream output of one furnace achieving one gradient solution. The substrate self-sufficiency figure measures the entire downstream conversion at industrial scale. The gauge on the growth furnace is not the same gauge as the one on the polishing line. Running alongside the crystal gain, and in the opposite direction financially, is the domestic price war. In 2022 and into early 2023, Chinese SiC device producers were pricing at a premium to imports. The argument to domestic electric vehicle manufacturers was supply security. Pay more for a domestic substrate and you are not dependent on a foreign supplier who might face shipping disruption or policy pressure. That argument worked while scarcity pricing held. It does not hold now. By 2024, multiple domestic producers were competing aggressively on price in electric vehicle inverter and fast charger segments, and margins across the sector were under significant pressure. The cost argument that made larger wafers strategically valuable, cut die cost per unit so the domestic producer can price competitively, is now racing against a market that is already cutting price per unit through volume competition rather than materials efficiency. The producers who invested in crystal growth capability are now competing on price against producers who sourced substrates from imports and invested instead in device packaging, sales networks, and customer relationships. The capital-intensive substrate players, the ones running the physical vapor transport furnaces, solving the gradient problems, growing the record boules, are competing in a market that is rewarding cost reduction through any available means, not specifically through substrate self-sufficiency. The efficiency gains from larger wafers still matter. They are now captured as survival margin rather than as profit that could fund the next capital expenditure cycle. Growing the substrate self-sufficiency figure from 20 to 30% towards something meaningfully higher requires capital investment in slicing equipment, polishing lines, and inspection throughput. That investment is hardest to fund at exactly the moment the price war is compressing the margin it would come from. The crystal record and the price collapse are not separate stories. They are the same story measured on two different instruments simultaneously. 3 readings deserve qualification before the synthesis. The 14-inch figure is a company disclosure on a single growth result. It is not a production yield number. A single successful boule at record diameter does not tell you the yield rate on subsequent runs, the defect density in the finished crystal, or whether that diameter is stable across the full temperature profile of a complete growth cycle. The instrument reads the best result on record, not the average result across a production batch. Second, the 20 to 30% substrate self-sufficiency estimate is an analyst range derived from import flow tracking and domestic production disclosures. It is not a verified customs figure or an independently audited supply chain count. Chinese producers do not uniformly report substrate sourcing by origin, and import reclassification can shift the number without shifting the physical supply. The range is the honest reading. A single point within it would carry false precision. Third, silicon carbide is among the hardest materials commercially grown as a single crystal. That hardness is the source of its value in power semiconductors and the source of the difficulty in converting a boule into a finished device-grade substrate at production yields. A 14-inch crystal is an upstream achievement. A polished, inspected, device-ready wafer at economically viable yield is a downstream achievement that the diameter reading does not address. The gap between those two achievements is where the self-sufficiency figure lives. Together, those three qualifications produce one synthesis. The 14-inch number is real, the 20 to 30% is a range on a number that is also real, and they describe an instrument with two needles pointing in different directions at the same time. One needle climbed 2 inches in a year. The other needle has moved, but it is still reading well below the threshold where domestic substrate supply would stop being a strategic vulnerability for Chinese device manufacturers. The honest reading holds both needles. 2 inches of additional crystal diameter on furnaces that no export list would have cleared, in the same year that domestic SiC prices are falling fast enough to compress the margins that would fund the next step. The diameter gain is real. The proprietary furnace is real. The self-sufficiency figure is real, and it is not the same number as the crystal record. The restriction that aimed at preventing the furnace from being sold produced the engineering that built it. That is the mechanism the diameter reading documents. Whether that engineering translates into supply chain depth or remains a material science record is the question the self-sufficiency figure will answer, and it has not answered it yet. The furnace is now domestic. This is now, whether the supply chain follows it, that is the reading this instrument has not yet given. By the end of 2026, will the domestic SiC substrate self-sufficiency figure move above 30%? Or will the price war consolidate the sector before the capital is available to scale it? That count, when it comes in, is the one that will tell you whether 14 inches change something structural or only change the record. If you want that reading when it arrives, subscribe and turn on notifications. This channel reports the count, not the claim.